In this video, we'll finally learn a little bit about this famous L'Hopital's rule. So L'Hopital's rule is named after a French mathematician whose last name was L'Hopital. And there's some different spellings of it. One looks like that La Hospital. I think the way that I have it written here, it really needs that little, whatever that symbol is that goes over there. But either way is pronounced L'Hopital. So if you remember, some of these limits we've done before, we spent a lot of time talking about the squeeze theorem, and we said that the limit as x goes to 0 of sine x over x was an important limit, and you just had to remember that it's going to be 1. And we'll see how to do this really easily using L'Hopital's rule in just a couple minutes. This other limit in the yellow, the limit as x goes to 2, if we direct substitute in 2, we get 4 minus 4 is 0 over 0, which is indeterminate. And our trick for resolving this was to factor that x squared minus 4 as the difference of two squares. And then we can cancel that thing that is causing that 0 over 0. Once those are canceled, we're free to direct substitute in the 2, and we'll get that the limit is 4. The green one, the limit as x goes to 0 of square root of x plus 4 minus 2 over x. When you direct substitute in 0 here, you also get 0 over 0, which is, again, what we call indeterminate. I'm going to write that down. So the trick that you do on this one is to multiply top and bottom by the conjugate. So we want to make that radical become the difference of two squares. So when we do that, the numerator is going to become the first term squared minus the second term squared, and then we'll just leave the denominator factored for a moment here until we let things work themselves out. So the 4 and the negative 4 will cancel each other. And then once they're out of the picture, the x's can cancel each other. Then it's safe to direct substitute in that 0 for x, and we'll get 1 over the square root of 4 is 2 plus 2, so that will end up being 1/4. So those are ways that we have resolved this indeterminate form 0 over 0 in the past. And now we're going to turn to L'Hopital's rule, which gives us some more firepower. So L'Hopital's rule says if f and g are differentiable, with f of a equal to 0 and g of a also equal to 0, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of the derivative of f over the derivative of g, provided the limit on that right exists. So there's a little bit to unpack here. So before we can use this rule, we have to know that the functions are differentiable and that when you plug in that limit point into each of them, what you get is 0. And they've gotten to be a real stickler about this on the AP exam in the last 3 or 4 years. So if you don't state that the conditions are satisfied, you are not going to get the points on this problem on the AP exam. And the other thing to watch out for is this, and we'll talk about this a little bit later. We're going to see an example or two where we satisfy the conditions for L'Hopital's rule, but then after we take the derivative of the top over the derivative of the bottom, the limit doesn't exist. In that case, L'Hopital just doesn't work, and we're going to have to try to figure it out using other means. Now, we should also state, too, that this can be repeated. So that is, if we get 0 over 0 on the first try, we can use L'Hopital's rule. Now, notice this is not a quotient rule. This is a derivative over a derivative. Now, if this ends up being 0 over 0 again, you can repeat it as many times as you need to until it does get resolved. That is, you could take the limit as x goes to a of f double prime of x over g double prime of x, and so on. Okay, well, let's revisit this sine x over x, which was one that we were just going to try to remember, and now we'll see that, and here's the way you're going to have to write it to satisfy the AP grading people. So you can see in your head, it's okay to say, oh, that's going to be 0 over 0, but this is not going to be acceptable. So what you can do is say that f of x is equal to sine x, and g of x is equal to x, and f of 0 equals 0, and so does g of 0. Now you have satisfied the conditions for L'Hopital's rule, so that means we can now take the limit as x goes to 0 of their derivatives. So the derivative of sine is cosine, and the derivative of x is 1. Just a little note here again, the AP is also very picky that every time you do this, you have to rewrite that limit notation. If you don't, you will not get the points. Now we can direct substitute in the 0 and see that the cosine of 0 is 1, and therefore our limit is 1. Okay, let's see what happens on the green one. If we plug in 0, we get e to the 0 minus 1. Well, that's 0 over 0, so that's 0 over 0, which is indeterminate. We can't write it that way. We're going to say, and if you want, you can even say this is f of x, and this is g of x, and say that f of 0 is 0, and so is g of 0. Oh, and I forgot to mention on the last one, you have to say what you're doing here. So you need to say that you are invoking L'Hopital's rule here. So this part satisfies the conditions for L'Hopital. Then you have to tell the people grading your test that you are using L'Hopital's rule to get now the limit as x goes to 0, and the derivative of e to the x is e to the u times the derivative of 2x. The derivative of 1 is 0, and the derivative of x is 1. Now we can direct substitute in the 0, and again, e to the 0 is 1 times 2 is 2, and so our limit is going to be 2. Okay, let's try the blue one. So if we direct substitute in the 0, we can see we're going to get e to the 0 is 1 minus 0, and we get 0 on the bottom, that's 0 over 0. So we're going to say that this is f, and this is g, and that f of 0 is 0, so is g of 0. So we have satisfied L'Hopital's rule. Now we're going to invoke L'Hopital. So we will take the limit as x goes to 0 of the derivative of e to the x is e to the x, the derivative of 1 is 0, and the derivative of negative x is negative 1, and the derivative of x squared is 2x. So if we direct substitute in 0, we get e to the 0, which is 1 minus 1 is 0. Uh-oh, we got 0 over 0 again. So we'll name this as a new f and a new g, and we'll see that f of 0 is 0, and so is g of 0. So we will use L'Hopital a second time. So now we're going to get the limit as x goes to 0. The derivative of e to the x is e to the x. The derivative of 2x is 2. Now when we direct substitute in 0, we get 1 over 2, and that is our limit. Okie doke. Trying the red one. If we direct substitute in 0, we're going to get 0 minus the sine of 0, which is 0, over 0 plus the sine of 0, which is 0, so it looks like it's indeterminate. So we will call this f and this g and say that f of 0 is 0, and so is g of 0. So we will use L'Hopital's rule, and that's going to be the derivative of 7x is going to be 7. The derivative of sine x is cosine x. oops, I didn't leave much room. I got to say limit as x goes to 0 over 2x, and now we're going to get the chain rule derivative, cosine of 3x, times the derivative of 3x, which is 3. Now we can direct substitute in the 0. 7 is still 7, minus cosine of 0 is 1, over 2 times 0 is 0, and 3 times cosine 0 is 3. So that's going to be 6 over 3, which is 2. There's our limit. Okay, let's look at the next panel. So it turns out that L'Hopital's rule also works for indeterminate forms that look like whatever flavor of infinity you like over infinity. So that can be positive infinity over positive infinity over negative infinity over positive infinity, or negative infinity over negative infinity. Any of those are candidates for L'Hopital's rule. So, but that doesn't necessarily mean it's the best way to go. But let's take a look at these. So on the first one, if we see that x grows large without bound, then this 5x is going to go to infinity. This, do you see that that's going to be 1 over e to the x? And as x gets really, really large, that's going to be 1 over a huge number. That's actually going to go to 0. So my thinking is that you could say this is going to go to 0, and without using L'Hopital's rule, we could say this limit is going to be 5/7, and I think that would be easier. But we could say, let's see what it looks like for L'Hopital's rule. So we can say that the limit as x approaches infinity of f is infinity, and so is the limit as x approaches infinity of g. Let's see what L'Hopital's rule is going to do for us. So the derivative of 5x is going to be 5, and then it's going to be a e to the u du, and then we're going to get 7 in the denominator. Now, as we take that limit as x goes to infinity, we're going to see that this thing is going to go to 0, and we're going to get our 5/7. But like I said, I think that would have been easier to do right from the get-go without using L'Hopital's rule. So you don't have to use L'Hopital's rule. Similarly with the green one, I would see this as an order of magnitude question. We know that an exponential is going to get bigger faster than any polynomial because it's a higher order magnitude. So I would just say that's going to be 0, and I would just say because an exponential is a higher order magnitude function than x squared. But we can say, let's play the game here a little bit so you can see what's going to happen. We can say this is going to be f, that's going to be g. The limit as x goes to infinity of f is infinity. So is the limit as x goes to infinity of g. So we can invoke L'Hopital's rule. That's going to, I need room to write my limit. So we'll say limit as x goes to infinity. That's now 2x over 2e to the 2x. This is going to be our new f, our new g, and again, we see limit as x goes to infinity of f. 2x is still going to go to infinity, and the limit as x goes to infinity of g is also going to be infinity, so we can do L'Hopital a second time. So now we're going to get the limit as x goes to infinity of 2 over, that's now going to be 4e to the 2x. Now what happens is we get a constant over something that's growing large without bound, and that's going to be 0. Not the most efficient way on that one. I would argue the same thing here, that we know that x is a higher order magnitude function than a natural log, so that is going to go to infinity, or we could say does not exist. But we can do it using L'Hopital's rule as well. I don't think it's the most efficient, but we can say the limit as x goes to infinity of f is infinity, so is the limit as x goes to infinity of g. So we can use L'Hopital, and we'll get the limit as x goes to infinity of, so the derivative of x is 1, and the derivative of natural log x is 1 over x, which, if you simplify, is going to be 1 times x, which is going to be x, which is going to go to infinity, so the limit does not exist, using L'Hopital's rule. Now, the next two are a little bit more interesting. But really, I don't think L'Hopital's rule necessarily helps us much with this. I think we're better off just reasoning our way through it. So a logarithm base 10 over a natural logarithm as x goes to infinity, what's going to happen there? What we want to do here is to do our change of base on this logarithm base 10. So if you remember, that's going to be natural log x over the natural log of 10. So when you simplify that, that's going to be the limit as x goes to infinity of the natural log of x over the natural log of 10 times 1 over the natural log of x. So you can see that these are going to cancel each other out, and what we get is this funny number, 1 over natural log 10, and that's our limit. Now, likewise, I don't think L'Hopital's rule is going to help us much on this next one, but if we use our properties of exponents, we can say that e to the x over 3 to the x is e to the 3 over x. Now, if we think about that, e is roughly 2.7. That is, it's smaller than 3. Now, if you take a number that is less than 1, which is what 2.7 over 3 would be, that's a number less than 1. Every time you multiply it by itself, it gets a little bit smaller. And so this, as we let x go to infinity, is going to get smaller and smaller and smaller and approach 0. Okay, now this next group is challenging because we're going to see that L'Hopital's rule does not work for all limits. It has to be in the right form, but even sometimes when it's in the right form, it's not going to work. So we're going to take a look at these. First, the yellow one. So here, as x goes to 3, if we direct substitute this in, remember we get 3 over 0. Now, we don't really mean we're plugging in 3 because the limit says what happens as we get close to 3. So as we get close to 3, what we're saying in the denominator is that's getting smaller and smaller and smaller. And so when you take something that is not going to 0 and divide it by something very, very small, what you get is something very, very large. Now you have to be a little careful. It's not going to be correct here to say it goes to infinity, because it's going to, no, I'm sorry, it would work here. So no matter which side of 3 you come from, number's a little bit bigger than 3 or a little bit smaller than 3, it's going to go to positive infinity. But it might be safer to just say it does not exist. But L'Hopital's rule does not even apply because that is not 0 over 0. The next one is tricky. So if we look at this, as x gets really, really large, if we call this f and we call this g, it is true that the limit as x goes to infinity of f does go to infinity, and so does the limit as x going to infinity of g. If we use L'Hopital, though, let's see what happens. We're going to get the limit as x goes to infinity of 3 over, and that's going to become a 1 plus cosine x. Now, we have to be careful here. As x gets larger and larger, this is not getting closer and closer to a single number. In fact, because this cosine is just going to bounce around between -1 and 1. When it goes to -1, then it's going to make this denominator go to 0, and this thing is going to kind of spike up to huge numbers, and we actually go to infinity right at pi over 2, or at any odd multiple of pi over 2. Other times, cosine is going to be 0, and this whole thing will be 3. Other times, this thing will be a positive 1, and it's going to be 3/2, and all the numbers in between. So this limit is not getting closer and closer to anything. It does not exist. Now remember, back in our definition of L'Hopital's rule, we said that if this was 0 over 0 or infinity over infinity, and you could take the derivative of the top over the derivative of the bottom as long as that limit existed. But this is a case where that limit does not exist. That means L'Hopital's rule cannot be used here. But we don't really need it. Let's go back and look at this and reason our way through it. Now, as x gets really, really big, these things are getting very, very large. Think 1,000, 1,000,000, 1,000,000,000. This sine x, it's just bouncing back and forth between -1 and 1 and all the numbers in between. But compared to these huge numbers, like when you plug in 1,000, 1,000,000, 1,000,000,000, that is insignificant. So this is going to act like, as x gets very, very large, it's going to act like just 3x over x, which is 3. And that is, in fact, the limit. Okay, so you have to be careful. The blue one is similar to this. So if we try saying this is f and this is g, it is true that the limit as x goes to infinity of f goes to infinity, and the limit as x goes to infinity of g is also infinity. But when we take L'Hopital's rule, we're going to get 1 minus cosine x. I need to take the limit as x goes to infinity over 1 plus cosine x. Now here we have that same issue because these cosines are bouncing around between 1 and -1, and they are not getting closer and closer to any single number. For some choices of x, when cosine is equal to 0, you're just going to get 1 over 1. Other times, when cosine is, say, a positive 1, you're going to get 0 over 2, you're going to get 0. Other times, you're going to get, when cosine is -1, you're going to get something that's approaching infinity, because you're going to get a 2 on top and something approaching 0 on the bottom. So this limit is not getting closer and closer to any one number. It is, and it's not in a form that we can continue to use L'Hopital's rule, because it's not 0 over 0, nor is it infinity over infinity. So this means that L'Hopital's rule just doesn't work. But we don't need L'Hopital. Let's reason our way through again like we did before. As x gets really, really big, then imagine 1,000, 1,000,000, 1,000,000,000. These x values are going to be these huge numbers, but this sign and the sign in both the top and bottom is stuck being something between -1 and +1. Compared to those huge numbers, x, they're insignificant. So I'm going to, I don't want to say equal, I'm going to say it's going to, I'm going to put an arrow. It's going to look like the limit as x goes to infinity of x over x, which is just 1. And that is indeed our limit. All right, very good.